Hi kids, hope you guys are all doing well out there. So what we're going to try, we'll see how this goes, but what we're going to try is me just videoing some lessons. And you can of course listen to the video as I go through the lesson with you. And then I'll give you a little assignment at the end. And then my hope is that I will also record a video of myself going through the assignment, which you can watch if you want to make sure you're doing the assignment correctly, or if you have any questions about the assignment. As of right now, my understanding is that this is all 100% completely optional. We're still trying to figure out how this is all going to look. So at this point, I'm just doing this for students who are concerned that they're, not learning math, that they're getting behind, that actually learning math is important. So if you're one of those students, then go ahead and watch this video and do what you would like to with it. All right? Okay, so we are starting chapter 6 today, which is on exponential functions. And so today we are going to just talk about some of the basic features of an exponential function. So to start with, just like linear equations have their own equation that we're all familiar with, y equals mx plus b. We also know that quadratics have their own equation that we're all familiar with, y equals ax squared. Sorry, man, this is going to be, hopefully by the end of this I'll be better at writing with the mouse, but we're all going to have to be patient right now. So this one right here is the general form of a linear equation. See if I move the mouse to the, nope, that's not going to work. Hang on just a second. Okay, that is the general form of a linear equation. This is the general form of a quadratic equation. Oof, that's worse. Okay, and so what they're giving us is the general equation of an exponential function. That is y equals some number a times some other number to the x power. And so what's unique about an exponential function is that for the first time in a function that we're studying, the variable is the exponent. So right here in a linear equation, you know that you're multiplying by x. Right here you do have an exponent, but it's a constant, it's a 2. This time the variable is going to be an exponent, and so that's going to change things considerably. All right, so a and b are the constants like it says. A can't equal 0 because if it equaled 0 then everything would cancel and we'd just be left with y equals 0, which is really boring. B has to be greater than 0. I imagine we'll talk about that a little bit more later as it comes up, but generally speaking, the reason for that is that if you are taking a negative number and raising it to a power, then the output values go back and forth between being positive and negative, and that would really cause a little bit of a mess. So we need the b value to be positive. And then also b can't equal 1, because if you raise 1 to any power, then you always just end up with 1. So that wouldn't be a very interesting function for us to study. Okay? All right, so that's the general idea. Let's take a look and see some of the key features of a exponential function. So I'm going to try something a little different here. Be patient with me, please. We'll figure this out. All right, let's try it this way. So if I want to figure out the domain of the function above, the domain, of course, I'm sure you remember, is all of the x values that you can use in the function. And since you can raise a number to any power, either a positive number or a negative number, the domain is all real numbers. And some of you all like to write that as negative infinity to infinity. Let's see if there's an infinity up here. Let's go to math. Yeah, so we could go instead negative infinity to infinity, and that would be the same thing. Okay? All right, then the range of the function. So the range is the output values, and we usually get the range of a function by looking at a graph. So let's do that. We could, oh, no, I don't have internet right now. So normally we'd go take a look at that on Desmos. So I'll just make a graph here by hand. So y equals 2 to the x. If I plug in 0, anything to the 0 power is 1, so we know it's going to cross the y-axis at 1. And then if I go 2 to the first power, I would get 2. If I go 2 to the second power, I would get 4. And if I go 2 to the third power, I'm doubling every time, so now I would get 8. So you can sort of right away see the distinguishing feature of an exponential function, which is that it increases very rapidly, because in this case we are doubling every time. So we can get a sense here that the range is going to continue on up forever to infinity. How far down will the graph go when we go this way? Well, let's think about what happens when you raise a number to a negative exponent. If I go 2 to the negative 1 power, that's really 1 over 2 to the first power, which would be 1/2. If I go 2 to the negative 2 power, that's really 1 over 2 squared, which is 1/4. And so what you can kind of see here is that since I'm doubling every time as I go this way, if I move to the left, I'm doing the opposite, I'm cutting it in half. And so the fun thing about cutting things in half is that no matter how many times you do it, you will never end up at 0. So in this case, my range will be 0 to infinity. And we've talked about the open brackets versus the closed brackets before. In this case, it's important because I can never actually get an answer of 0 when I plug numbers into this exponential function. Even if I go 2 to the negative million, it's still going to be 1 over 2 to the million, which will be a super, super small number, but it's not ever going to be 0. Okay? All right, so what about intercepts? The y-intercept you can see from looking at the graph, or also you can just remember that you get the y-intercept by plugging in 0 for x. So our y-intercept is going to be at 0, 1. And then our x-intercept, where it crosses the x-axis, is nothing, doesn't exist, because, like I said before, this function will never equal 0. So the x-intercept equals none, nunca. Okay, asymptotes. Feel bad not being in the classroom with you guys. There's so many joke opportunities that are passing by me, but we would be having a lot of fun with this if we could be having this conversation, but we'll just all have to adjust. Anyway, asymptote, you can see that the graph levels out at the negative x-axis, so we're going to have an asymptote at y equals 0. Even though it goes up over here, that's still an asymptote because it goes in one direction. And then since this is increasing forever, that's all we're going to get. And then our end behavior is that, I don't know if I can write this with the little tool that I have here. Let's see, as x, see how fancy we can get, as x approaches negative infinity, then we can see that the y values approach 0. And then also as x approaches positive infinity. So as the graph moves to the right, then the y values approach infinity. So it gets bigger and bigger as it goes to the right, but then as it goes to the left, it just bottoms out at 0. All right? Okay, so that's the general idea behind an exponential function. What a beautiful graph I drew there. That's clearly a work of art. Okay, so let's change some of those numbers and see how that changes the graph and our answers to all those other things. So let's take a look at the graph real quick. Once again, if I plug in 0 for x, anything to the 0 power is 1, but this time I have this 5 out in front here. Notice on this other graph here I didn't have a number in front there. Now I have a 5 out in front, so if I go 1/2 to the 0 power I get 1, and then 1 times 5 is 5, so this graph will cross the y-axis at 5. Then if I plug in 1, 1/2 to the 1 is still 1/2, and 5 times 1/2 is 2.5. So now you can see as we're moving to the right, instead of the values increasing like it did in our previous graph, now the values are decreasing as we go to the right. So this one gets cut in half, the next one is going to be half of that, and half of that, and so forth. Same thing was with the other graph. I can keep cutting things in half as many times as I want, but I'm never going to get to 0. So this graph is going to bottom out there. And then this time if I go the other direction, instead of cutting things in half as I did when I go to the right, I'm doubling things as I go to the left. And so the graph is going to look something like that. All right, so now that we have the graph drawn, we can figure out all the different things they want us to figure out. The domain of this function will once again be from negative infinity to infinity, all real numbers. And then the range of this function is just like it was before. X is greater than, y is greater than 0, which we could also write as 0 to infinity. And then this would be the place where one of you astute students would ask the question, will the domain of an exponential function always be all real numbers? And will the range of an exponential function always be from 0 to infinity? And then we'd get to have a really fun discussion about that, and some dojo points would be awarded, and happiness would rule the land. But unfortunately, we don't get to have those face-to-face conversations. So let me just answer those questions for you. Will the domain of an exponential function always be all real numbers? Short answer is yes. The range, however, will change because, as we'll see later, if I add or subtract values to this graph, or to this function, I can move the graph up or I can move the graph down, and so that will affect the range, okay? All right, so then the intercepts is what comes, no, I don't want to do that. The intercepts are what comes next. So the let's do the y-intercept first because that's more interesting. The y-intercept, you can see from this graph, is not 0, 1 because of this 5 right here. The y-intercept for this graph is 0, 5, which might lead some of you to ask the interesting question, will this always be the y-intercept? And the answer to that is absolutely, so that's exciting to think about. And then the x-intercept, of course, for this one will be none. Again, we could have a conversation about will that always be the case? And the answer is not necessarily, because if I move this graph down, then you could see that this would cross the x-axis. So it depends on whether there's a vertical shift here or not. Okay, so let's see, what else do we have? Asymptotes. Hello, where are you? Asymptotes. This one has the same asymptote as the other one, which is y equals 0. And then the end behavior is the same as the other graph also, except for now it is flipped around. So in this case, as x approaches negative infinity, you can see that the graph is now going up. So as we go to the left, as x approaches negative infinity, the graph is, the y values are also approaching infinity. Because if we go this way and do negative x values, then the y values are increasing. And then if we flip this around and talk about what happens as x approaches regular old infinity, then you can see from looking at the beautiful graph that I have drawn that y will be this time approaching 0. So basically what we have done by changing the 2 from the previous graph into a 1/2 on this graph is we've just flipped it around. Alright, so that's what an exponential function looks like. Okay, so if you wanted to, you could take a second, pause the video, get out a piece of scratch paper, and try this on your own. Take a look at the graph of y equals 4 times 0.5 to the x. Maybe just make a sketch of that graph and figure out what the domain, range, intercepts, asymptote, and end behavior are for this function. So if you want to do that, go ahead and pause the video and do it. All right, welcome back. Hopefully that was fun for you. Let's draw a little, ooh, that was a bad one. All right, come on, let's get serious here, Aldrich. Okay, so white, that's a good color. I'll get through this. All right, so here's the x and y axis, and let's see, if I plug in 0 for x, 0.5 to the 0 is 1, 4 times 1 is 4, so there's that relationship between the a value and the y-intercept showing up once again. If I plug in 1, 0.5 to the 1 is 0.5, 0.5 times 4 is 2, so you can see hopefully pretty quickly that we are once again in the situation where as we go to the right, the y values are being cut in half, which means as we go to the left, all of the y values will be doubling. So here's the graph for that. Which means I'm not going to write it all out, but the domain, once again, is negative infinity to infinity. The range is 0 to infinity. Remember, we need open brackets around the 0 because it can't equal 0. The intercepts, the y-intercept is 4, this number right here. The x-intercepts don't exist. The asymptotes, we have an asymptote once again at y equals 0. And the end behavior for this one is as x approaches infinity, y gets closer to 0, and as x approaches negative infinity, y gets closer to infinity. Okay? All right, so now let's add a couple more shifts onto here. You all know, remember, and understand, I'm sure, what happens if you put a negative in front. Yes, I would love to be able to call on someone to answer this question, because I'm sure all of you watching at home are enthusiastically raising your hand in front of your computer. But the negative in front of the function will flip the graph upside down. Okay? So that's a, let me see here, what's the best way? Insert. So this is going to give us, as always, a reflection across the x-axis. Okay? And again, that's because of the negative here in front. Let's see, how do the asymptotes intercept a given function? Okay, so the asymptotes are the same. This is still y equals 0, which is what the parent function would be. This is the parent function right here, so what we're doing is we're starting with y equals 3 to the x and messing around with that. Let's see. And then the intercepts, so the intercept of the original function would be 1, because there's a 1 there that we just don't write, but you always assume that it's there. So in this case, there would be a 1 in front of here also, but because of a negative, that would switch the y-intercept to be -1, okay? All right, if we take a look at this guy over here, and it is the same thing, y equals 3 to the x, but it is -4. So now instead of crossing the y-axis at 1, which is where it would if that -4 wasn't there, the graph is going to get moved down 4 to, so it's going to cross the y-axis at -3, and then from there the function is going to look the same as it did before. Okay, so we would describe this as a, what do we call that, a vertical shift of -4. Or for those of you that like to use fancy pants language, you could just say down 4. How do the asymptotes? So the asymptote here, that's a little bit of an interesting question, because for our original functions that we graphed, original exponential functions that we graphed, the horizontal asymptote was at y equals 0. You can see that over there on this beautiful one that I've drawn. This time the asymptote got moved down 4 along with the graph, so that means our new horizontal asymptote will be at -4. OMG. And then the intercept was originally at 1 because of the 1 in front of the 3, but if we move that down 4, like I said, our new intercept would be -3. So in this case, both the asymptote and the y-intercept got moved down by 4. Okay? All right, what else we got here? Okay, so same dealio. If you want to pause the video and give these a try on your own, go right ahead, and then I'll do them in just a second. All right, so this first one has a little bit of a new look for us. This time we have a +3, but it is the +3 is in the exponent. So hopefully y'all remember that a +3 up there moves the graph left and right. You kind of need to think of this as being in parentheses. So this is going to take our original parent function that would look roughly like this and move it to the right 3, so it looks more like this, okay? Yeah, did I do that right? Oh, no, I didn't, sorry, to the left 3. Okay, so it's going to be like this, and then it's going to start going up before it gets to the y-axis, okay? So the graph looks something like that. All right, so what about the asymptote? The asymptote of this bad boy would be the same as the other one, because it just got moved left or right, not up or down. The intercept, however, is very, very different. Remember, you can always find the y-intercept by plugging in 0 for x. So in this case, if I plug in 0 for x, I would get 5 to the 3rd. So that means that the y-intercept of this graph will be all the way up at 125, which is 5 to the 3rd power. So good thing I didn't put a scale on my graph there, so you guys can't get mad at me for doing that wrong. And also, sorry, the asymptote is still at y equals 0, because we haven't moved the graph up or down. Okay, let's see how that compares to this guy over here. So now we have a negative in front of the x. That's exciting. Love to know if you remembered, anybody in class could remember what a negative in front of the exponent does. That flips the graph across the y-axis, so now my graph is going to look like this. And the reason for that is, we talked a little bit in the last chapter about negative exponents. 5 to the negative x is the same as 1 over 5 to the x, which is the same as 1/5 to the x power. Oh, that was bad. I'm going to go back when this is all over and I'm going to rewatch this video and laugh at myself for being so bad at writing with the mouse. I'm going to get so much better at this over the next 5 or 6 weeks. Okay, anyway, so 1/5 of the x power, that means that what's happening with this graph is as we move to the right, the y values are being cut in 1/5 every time. So that's why the graph looks like that. Okay, so then if we wanted to talk about the asymptote, again, the graph has not been shifted up or down, so the asymptote is still at y equals 0. And then to find the y-intercept, we would need to plug 0 in for x, and so 1/5 of the 0 power is just 1, so the y-intercept in this case is at 0, 1. Okay? Okay, so I feel like, because I just don't know how this is all going to go, let's call it good. That's probably enough for today. Like I said, I'm going to put some problems for you to do on the board here, but you're under no obligation to do them at this point. And I know, there's questions about, hey, what if when we get back? Some people have done the problem, some people haven't, and what do we do about all of that? And I just don't know the answer to any of those questions, and so we're just going to take this one step at a time. That's all we can do at this point. So if you want to do a little math, here's a little math for you to do. If you don't want to do a little math, then who could blame you? So hang on a second. Okay, let's all right, let's start with that, see how that goes for you. Like I said, my goal is later today to make a video of me doing these problems so that you can check your work. I know you guys have other ways of checking your work also if you wanted to. Feel free to send me an email or comment or whatever on Google Classroom if you need help or if you need words of encouragement. And we'll just see how this goes. Tomorrow, I don't know, maybe this isn't what we're going to do. Who knows? We'll figure it out. It'll be fine. All right. Talk to you all later.